Good evening, everyone. Welcome to the Mechanical Unit Operation course weekly discussion. Today we are discussing about gravity settling process. So it is also a very useful process in wastewater treatment and many other instances where we require clarification operation, where require clear liquid, or we wanted to separate it out solid out of the liquid. Okay, so let me share my screen and we'll start discussing for today. I hope everyone can see my screen. Yeah, okay. So this is a today's discussion on gravity sedimentation process. Mainly 3 lectures are there, and we are not covering each and everything like design of thickness and all, but as soon as important concepts as well as some example problem we will cover in today's lecture. If you find any difficulty, then you can reach out to me. Okay, we will start. So there are 3 lectures which professor took for this in this weekly discussion. One is a gravity sedimentation classifiers, or you can say the conceptual part and different equipment for that. Another 2 lectures on the design of thickness. Okay, and we are going to cover today gravity sedimentation process basic concept, gravity classifiers, not much in detail. There are 2 methods, sink and float method, differential method. Then some equations which are useful for you to solve the assignment problem and some in the exam related problems in your end final exam. Then some examples, clarifiers and thickness. And there are 2 different kind of sedimentation or this sedimentation process. One is in the batch process and another is a continuous process. We are going to cover all these topics today. Okay, so we'll start with the gravity sedimentation processes. So as it is mentioned that gravity sedimentation processes are impaired by the force of gravity. It is already mentioned in the name itself that gravity sedimentation will cover use the force of gravity to separate it out solid particle from the slurry. In such process, the fluid may be at rest or flowing at a certain velocity. There are mainly two types of gravity settling process. In one process, fluid is in the static mode and you can separate out the fluid from the bottom. In another process, fluid is in the motion and we can able to separate it out from the slurry. Solid can be separated out from the slurry. So our main purpose is to remove the solid particles by using the gravity from the slurry or suspension. Now, what are the objectives for using gravity sedimentation process? First objective, if in some operation we have to remove the particle from a stream in order to eliminate the contaminants from the fluid. So mainly wastewater treatment where we want to remove solid particles, solid garbage or sludge from the liquid, and we want some clear liquid at the end. Then gravity sedimentation is must to go process for that. Sometimes we want to recover the particles, as in elimination of the dust and fumes from air or flue gas. Sometimes our fumes or flue gas has some dust particle, we want to remove it. Then also gravity sedimentation can be work sometimes. And the important example is to remove objective is to remove the solid from the liquid waste. So in some other problem, particles are deliberately suspended in the fluids. So if you want to separate the 2 different kind of solid mixtures are there, if you wanted to separate it out, then we have to convert into the fluids or slurry form or suspended solid form, and then we can separate it out by using this gravity sedimentation process. So this is also another area where this gravity sedimentation processes are going to use. So here, to obtain the separation of the particle into fractions differing in size or density, or if you want to recover the fluid, then also we can go for the okay. So today we are discussing the gravity sedimentation process week 10 lectures, and these are some basic concept, and then we will go for the equations and some example problem solving. So because there are conceptual questions are available in the in the assignment problems, that's why we need to understand some basic concepts behind this gravity sedimentation processes. So as you can see here, our objective is to remove the particle from a steam in order to eliminate contaminants, or we want to separate it out the dust or fume from the air or flue gas and the waste water treatment, which is a much more important example for the gravity sedimentation. But sometimes we have two different solid particle mixture and we want to separate it out into the different sections or different fractions. Then also we can convert them into the slurry form by using some fluid, and then we use this gravity sedimentation process to recover it into the different fractions. So I just wanted to play some small less than 1 minute video where you can see how this gravity sedimentation process or thickener can work. It is also known as a thickening process. So as this is only, you can see that, okay, maybe we can pause it here. So as feed is coming, and as you can see, this is the big agitator which is agitate the whole mixture at very slow pace, and as you can see, we feed has a slurry here, and then it can go through to this whole equipment, or you can say thickeners, and then depending on to the, as name suggests, it's a gravity sedimentation. So depending on to the mass of the particle, the settling process is going on. Okay, sorry. So the heavy particles are first settled first, and then the small particles afterwards. And as you can see, the settling of solid make the sludges. Okay, maybe I should not have to touch in the video, otherwise it is always making some problems. So as you can see, that settling of solid is taking place, and after some time you will get a thick layer of sludges there. So this overflow, you will get the most clear liquid. We will add water also. Sometimes in the slurry, if you want to go for water, is a very useful solvent in this kind of sedimentation process. But although if we are not using water, then also we are using sometimes water additionally. And suppose here they are using already water, so water is coming into the overflow, and you can get clear water at the end. So it's a very simple process. We are using just gravity to settle it out. Okay, that's it. Okay, so I have one another video where they again discuss the process as well as equipment in a little bit detail. So this kind of arrangement is always present in the where most of the wastewater treatment plants are there. So as you can see, so fluid is coming, and agitation is going on, and overflow, in the overflow you are getting the pure water, and at the end, in the below, underflow material is consists the sludge, heavy sludge, and it's very thick liquid. So this is a just small animation that how this process is taking place. So because going into the much more conceptual detail, this small details you need to take care of it. Okay, that's it. Now, what are the principles of gravity separation? They are mainly based on the flow past solid objects. So in the past lectures we discussed that what are the different types of force acting when flow is passed to the solid objects. Another, when the solid particles are flowing into the immersed into the liquids. This kind of lectures we already covered. So that's why we have some terminal velocity concept in our mind to solve the similar kind of example, because here also we are dealing with solid particles as well as liquid particles. So here it is mentioned that if a particle starts at a rest and is then moved through a fluid by an external force, then two stages of motion can be seen. So once when we start the solid particle will start obviously at a rest, and then you are providing the agitation. Then there is a two kind of different motion is taking place. In the first, short period of acceleration is there, which increase the velocity of solid particles to 0 to the terminal velocity. Terminal velocity is the velocity where you will not get any more acceleration. It is a constant velocity for the settling of the particle. We discussed in this concept before. And another is, first it is takes some time to achieve that terminal velocity in the liquid, and after that the velocity is constant. So this is that period where a short acceleration is there, and after that the constant velocity is there. dv by dt is equal to 0. There is no change. So initial accelerations, now sometimes this initial acceleration is much more important in order to separate out the particles in the different fractions. So that's why in some operation this initial acceleration is learned into the great interest, and according to that design of the equipment is taken place. So initial acceleration effects are short range, obviously, because it only covers the short span of the particle, traveling of the particle. Whereas terminal velocity, once it achieves the terminal velocity, where its velocity will be constant and there will be no any change in it, it can be maintained as long as the particle is under treatment. Now in the so there are some questions of how we based on the operation of the devices. So you have to keep in your mind that some operations such as jigging as well as tabling. There is two different kind of operation. Mainly for the separation of the particle size is different particles is taking place by using this gravity separation. One is a jigging and another is a tabling. So in that, difference in the particle behavior during the acceleration period is much more important. Okay, so the first part where we take care of this increasing of the acceleration in the short span, it is more important when we just want to separate our solid based on the different size of the solid fraction. So this difference in acceleration period is important. According to mass, heavy mass particle has more acceleration. It is much more settling faster than the small particle or particle which has less mass. There is another operation, the settler, that removes virtually all the particles from liquid, is known as a clarifier, which is mostly used in a wastewater treatment. There are many sedimentation techs are there. And there is another operation where device that separates the solid into two fractions is called a classifier, such as dust and collecting chambers. So classifier is also one use where we are using this kind of operation. Now gravity classifiers. Now we need to understand what is actually classifiers and how it is how we can use it for the gravity sedimentation processes. So gravity sedimentation is like in classifiers, that is separates particle into two fractions. Obviously you need to understand when we are talking about the classifiers, then it will separate particles into different fractions. And when we talk about the clarifiers, then it will use for the removing of the solid particle from the liquid. So there are one another terminology is clarifier and one is a classifier. So classifier, there are two different fractions, as they are separating the solid into two different fractions, also known as the dust settling chambers. These are the devices that separate particles of different densities and are known as the sorting classifiers. In other words, separation of particles into several fractions based upon their settling velocity is known as a classification, and equipment used as a classifier. Obviously, our main purpose here is separation of particles into several fractions based upon their settling velocity. Settling velocity depends on the gravity and other forces. So there are mainly two different principal separation methods are using when we talk about the classifier. One is a sink and float settling, another is a differential settling. There are mainly these two different methods or principles, separation principle, which are using in this classifiers techniques. Now, what is a sink and float method? Okay, so in the sink and float method, a liquid of intermediate density chosen, that the lighter material will float and the heavier items in the liquid. So suppose we have two two different solid. One has a density of 1000 kilogram per meter cube, another has density of 2500 kilogram per meter cube. So we will choose the liquid which has a density between in the period of in between the 1000 to 2500 kilogram per meter cube. So this is the way this sink and float method can be used. This method is independent of size of particle and depends only on the relative densities of materials. Here we only consider the relative densities. We don't have to worry about the size of the particles. For this method, liquid must have densities greater than water, since most solids have a high density. So obviously, when we are using this solid particle separation classification by using sink and float method, so we have to use the liquid which has a density which is more than water. So unfortunately, few such liquids exist in the economical and non-corrosive. So very few liquids are present in the world, so that we can use and design economically. So most of the times they are using the pseudo liquids. So pseudo liquids are the suspension. They are making the suspension in water of very fine solid materials, and depending on the required specific gravity. Most important or most popular pseudo liquids are made out of the water suspension of galena or magnetite particle, which are the solid particle only. We are making the water suspension and use as a fluid into the sink and most of the sink and float method or cavity sedimentation process. Then hindered settling is used due to presence of this suspension, and the bulk density of the medium can be varied widely by varying the amount of fine solid materials in the medium. So according to the use of fine solid material, the bulk density will be varied. Fine solid material in the medium are so small in diameter that their settling velocity is negligible, giving a stable suspension. So fine solid material in the medium are so small, so we need to understand the settling velocity is too much negligible for separation. So the example, concentrating one ore material in cleaning coal. So these are all about the sink and float method. We will switch over to the differential settling method. So differential settling method has density of medium is less than 10 of either of the two substances to be separated. Here we are using the density of medium, which we are using medium which has a density less than 2 of the materials. So what is the disadvantage of this? Smaller heavy particles at approximately the same terminal velocity as the larger light particle. So here you can see there is a graph of terminal velocity versus particle size. So A is a heavy density material and B is a light density material. So heavy, or you can say the larger light particle is has the same terminal velocity of the smaller heavy particle. As you can see, this is the terminal velocity versus particle size profile for B as well as A. So A is a heavy material, so you can say it is settled faster than the B. So it is required less time than it will require for the B. The particle size is depending on this terminal velocity. And you can see for this smaller particle size of the light density material, then there you can see this it required a much slower settling. Its velocity is too much slow, so it requires more time to settle down in the another material due to the gravitational force which is acted into the separation. Now equations. So we have terminal velocity equations in our flow past solid bodies, flow past immersed bodies, where we have terminal velocity U is equal to under root of 4g rho pa minus rho into dpa, 4 by 3 into g rho delta rho pa minus rho dpa upon cda into rho. So these are two different, if you consider the two different particles, then A and B you will consider as So just ignore this. In summary, if it okay, so we will not go into the whole derivation. There are two different types of study we can do. Summary for the particles of the equal settling velocity, and another is the particle of the equal diameter particles. So equal particles have equal settling velocity. If we talk about the Stokes flow region, there are mainly three regions. Stokes flow region, we need to depend on the value of K for that. K less than 2.4 is the Newton's region, or you can Stokes flow region. So basically you can understand this, all we discussed before. So Stokes flow regime, which is required that the ratio of the diameter is equal to under root of ratio of the density difference. So dPA by dPB is equal to under root of rho PB minus rho upon rho PA minus rho. You understand this. If you directly remember this formula, you please take care of this notation. They are not in the same side, they are the opposite side. If you talk about the Newton's flow region, then this under root will convert it into the linear relation. So dPA by dPB is equal to rho PB minus rho upon rho PA minus rho. If we talk about the intermediate region, then we can't say which power of density difference ratio will take place. So it may be varied upon vary between 0.5 to 1, as Stokes flow regime has a 0.5 and Newton's flow regime has 1. So it will be vary in between. So there is these equations we can remember for instance they are asking the problem in which equal settling velocity, particles of equal settling velocities are mentioned. If it is mentioned that particles of equal size, their velocity equal and here equal size are there, then the equations are based on the velocity. There are, if we talk about the velocity, same velocity, then ratio is going to for the diameter. Now we are talking about the diameter, then ratio is for the this terminal velocity. So you can say for the Stokes flow regime, terminal velocity ratio is equal to rho P minus rho upon rho P minus rho. It's same density difference, ratio of the density difference, but the power is different. So here power is 1/3. For Newton's flow regime, UTA by UTB is equal to under root of rho PA minus rho upon rho PB minus rho. For intermediate region, obviously this is a 1/2 and this is 1/3. So intermediate region is in between. Why you can say it's 1/2, not root 2? So here you can say that when we talk about the velocity, terminal velocity or equal size particles are there, then the notion of all the particles A and B are the same as the both the side of equal to, not same as the diameter ratio. For Newton's flow regime, it's under root 1/2, and for intermediate region, it's power of n, and the n will be range from 1/3 to 1/2. 0.33 less than equal to n less than equal to 0.5. Yeah. Now we will directly solve one example and understand how we will use this. Sorry. So here it is a similar example which solved from the professor, but it has different values. So mixture of silica and galena solid particles having the size range of 4.32 into 10 to power minus 6 to 4.25 into 10 to power minus 5 meter is to be separate. This is the lower particle size and higher particle size is to be separate by the hydraulic classification using free settling condition in water. Now we have galena as well as silica solid particles. So what are the specific gravity? It is mentioned that for the silica specific gravity 2.85, for galena it is 7.38. Now you have to calculate the size range for both the particles, for silica as well as for galena. What is the smaller particle size range or bigger particle size range, considering CD is close to that of the sphere? So we don't have to think for the CD. In the previous we discussed the examples only which is based on the spheres. So sphere CD value is equal to constant 0.44, and then it is when we are taking the ratio then it is cutting down from up and down. Now we will start the example. First we have we have to list out it. So here we are using the water. So for water, okay, density of this is not particle, this is a fluid. So what is the density of the fluid? It is 998 kg per meter cube. We can consider for the water. And what is the viscosity of water? Or here we consider water as a fluid. So viscosity is 1 into 10 to power minus 3 Pascal into second, or kilogram per meter into second. Now density of particle is 7.38, and we multiply with the 1000, approximately 1000. So 7380 kg per meter cube and 2850 kg per meter cube. Now we'll find that in which region our particles are or this process is taking place. So for that, largest size heavier particle, we only consider the largest particle here. So for that, dp is already, which is the largest one, we will take care of it. Dp is for the 4.25 into 10 to power minus 5. So 4.25 into 10 to power minus 5 is the value of dp. We will substitute. G is 9.81, density of 998 rho p. Here we will which density we will consider? We consider the 7380 because it is a heavier particle. This is a larger size, and this is a heavier because more density, maximum density. So upon mu square, we substitute the value and we will get the value of 1.680, which is certainly less than 2.5. That's why we can say that, okay, if our heaviest particle, which has a higher terminal velocity, which is comes under the Stokes regime, then our whole process where whole heavier and lighter particles comes under the Stokes regime. So this is a smaller understanding of our particle size distribution, which are considered when we are using the fluid. They are passing through the fluid. So we consider this is the terminal velocity versus particle size graph. So you can consider this is our heavier particle, which is settles faster. Then if we consider the largest particle size, which we mentioned at 4.25 into 10 to power minus 5 meter, if we consider as a dp4, okay, so dpa4 because its a is there. Then if you want to consider this is a dp4, okay, pure fraction, then we have to consider dpa3 minus dpa4, which will be our pure fraction of for a. And at the same time, we discuss about the smallest size, then we consider dp1, which is given as a 4.33 into 10 to power minus 6 meter, which is set as very slow, so it has a very low terminal velocity. And we consider for the b, so that's why dpb1 minus dpb2 will consist of pure b fraction. Okay, so now we have to find out this dpa3 by dpa4 and dpa1 by dp2, or dpb1 minus dpb2. So which is you can consider the smallest volumetric fraction and the highest volumetric fraction. Now for equal settling velocity, here it is mentioned that it has equal settling velocity. Now we have to rely on the diameter ratio. So diameter ratio, it is a Stokes regime, so we will go for the density difference, ratio of density difference under root. So dpa by dpb is equal to under root rho pb minus rho upon rho pa minus rho. Here we will consider dpa as a dpa3 because we want to go for the particle size of dpb4. So dpa3 minus dpb4 is equal to rho pb minus rho pa minus rho. Here we consider the largest particle 4.25 into 10 to power minus 5 as a dpb4, substitute the value, and at the end we will get a dpa3 is equal to 2.29 to 10 to power minus 5 meter. Now we will go for we will do the same calculation for the dpb. Now here we will get the value of dpa3, okay, by substituting the largest particle as a dpab4. So we will get the range for dp, like for the particle size a fraction will get 2.29 minus 4.25 into 10 to power minus 5. Now in the same for the B, then dPA1 by dPB2 is equal to rho PB minus rho upon rho P minus rho raised to half. Here we substitute the value of dPA1 as a small particle 4.33, and we will get the value of dPB3. You have dPB2, so it is like this. Now it is in the range of 8.04 10 to minus 6 to 4.33 into 10 to minus 6. Now size range of pure fraction of A is equal to dPA3 make 2.29 10 to power minus 5 to 4.2 10 to minus 5. Mixed fraction range, where we will get the smallest is 4.33 to 8.044 into 10 to power minus 6, then 8.044 to 4.2 into 10 to power minus 5. And if we talk about the pure fraction for B, then dPB1 is 4.33 into 10 to power minus 6 meter to dPB2 8.02 10 to power minus 6. We already discussed how it are coming. Okay, dP1, dP. Now in the another example, in the hydraulic classification, the density of medium solution plays a vital role for efficient separation. So, okay, so density is much more important. Assume mixture of silica which has density of 2280 kg per meter cube and galena of density of 920 kg per meter cube. Solid particles having a size range of 3.21 into 10 to power minus 6 meter to 8.21 into 10 to power minus 5 meter is to be separated by hydraulic classification using free settling condition in a liquid. Which of the following density values would be in the appropriate range for the density of the interliquid to be used in the separation, to be done by the sink and float method? Now we know that in the sink and float method, the density of liquid which we are using to make the suspension, which needs to be in between the size of both the two different solid particles. So our density of liquid must be between 920 to 2280 kg per meter cube. Okay. So this is the thing which we have to take care of. The questions, like, we don't have to solve anything if we know the answer directly. Like here they mentioned the liquid density which in between which of the sides. Then we have to directly consider that in sink and float method, obviously liquid must be between the density of those solid particles. So our density of liquid is between this both the particles, both the different density. So the density of liquid is between the density of both the solid particles. Now in the hydraulic, there is another example here. In the hydraulic classification, the density of the medium solution plays a vital role for efficient separation. Assume mixture of silica B and galena A solid particles having size range of 7.56 into 10 to power minus 6 meter and 4.25 into 10 to power minus 5 meter is to be separated by hydraulic classification. Here it is mentioned, we are separating hydraulic classification using free settling condition in water. So specific gravity of silica and galena is given 2.3 and 7.9 respectively. Calculate the size range of pure air fraction obtained in the settling. So we already have seen one kind of example for this size range of fractions for particular heavy particle and as well as the light particle. And here also we have to consider the CD is closed for the sphere, so we don't need to think about the CD value. Now we start with the dP ray diameter range is 7.56 into 10 to power minus 6 to 4.25 into 10 to power minus 5 meter. Density of particle rho PA, which is 7900 kg per meter, rho PB is 2300 kg per meter cube. Density of particles, this is not density of particle, density of fluid which we are using water. Density is 1000 kg per meter cube. Viscosity is 1 into 1.005 into 10 to power minus 3 pascal into second. Now again we need to find what is the value of K, because we want to determine that in which region the whole process is taking place. So K is equal to dP Gp rho P minus rho upon mu square whole is to 1 by 3. Our dP is highest particle, we will consider 9.81 thousand. Density is also, again we consider the heavier particle, largest particle and heavier density. Minus 1000, 1.005 into 10 to the power minus 3 whole square whole is to 1 by 3. At the end you will get the value of 1.726, which is less than 2.5. Again all the particles are under the Stokes regime. No, again we are using the same under root equation which has okay. So as we discuss about the Stokes flow regime, so okay, just I will again explain this example. So there mostly this kind of basic examples will be asked in the exam and assignments. There you have some size range of two solid particles and you are using some liquid to separate it out by using hydraulic classification. These words are very important to understand the types of problem, and that you will be given two different values. One is the size range from smallest particle size as well to the largest particle size, and another you will get the specific gravity of both the solid particle, where you need to separate it out into the different fractions. Now in some example they will ask you to find the heavier particle fractions, and some example for another light particle. Sometimes they will ask both. So this is common process you need to follow. Most of the time they will give you the CD value is close to the spheres. So CD for the sphere is 0.44, and at every time you will take the ratio. This will be cancelling out, and you will get the value of like directly ratio of the diameters. Okay, so we already discussed, but if someone joined now, so we will again discuss. This is our diameter range. Density of particle is given. You like specific gravity is given. You have to multiply with 1000 in order to get the densities. You will use the water as a fluid, which has a density of 1000 and viscosity of 1 into 10 to power minus 3 Pascal into second. So first step of our this kind of example is to find in which regime our process is taking place. So mainly there are two places we need to take care of it: Stokes flow regime or Newton's flow regime. So according to it, we have to find the value of the K, which if it is below 2.5, then and we will go for the Stokes flow, and if it is more than 68.5, then we'll go for the Newton's flow. And in between, intermediate region is there. So according to it, we will use the value of N. So for the Stokes flow regime, there is some typical value. Sorry, in the next set of calculation, we don't have to bother about all these things. So this is the equation: K is equal to dp g rho p minus rho divided by mu square raised to 1 by 3. Here we need to take the largest size and heavier particle. We have the particle size diameter range. We need to consider the largest size of particle, 4.25 10 to power minus 5 meter, and at the same time heavier. So density is also, when we talk about the particle density, we need to take the heavier particle density, which is a 7900 kilogram per meter cube. Other than that, fluid density is 1000. 9.2 is the gravitational acceleration constant, 1000, and you will substitute the value of mu. At the end you will get the value of 1K value at the end. It is, if it will less than 2.5, most of the times you will get the value less than 2.5. Then you have to consider the Stokes regime. In the Stokes regime, now how will you find out the size fractions? So Stokes regime, this is the equations which is given, and we will not we already discussed in the conceptual part in the earlier slides. So the ratio of the two different particle diameter is equal to the ratio of two different difference of density in the power of 1 by 2. Okay, so here you have to consider that you have to must keep in your mind that your this particle A is not in the same side in the both the side of equal to, it is a okay. If you don't want to see the lectures, then it's fine. So you can see that if you are taking the ratio, then this is the equation. Now if you want to go for the A, then you will consider the one value of A. Here we consider the both are A. If you talk about the one, consider the smallest particle. Oh sorry, largest particle, because A is a heavy particle. So you have to consider the largest particle, which is a dPa4, according to the chart we discussed in the previous example. So we will find the dPa3. You substitute all of the value and you will find a dPa3 1.85 to 10 to the power minus 5 meter. So this is your particle size range, 1.85 to 10 to the power minus 5 to 4.25 to 10 to the power minus 5 meter. Sorry. In the same example, sometimes this is the same example, this is the same size range, this is the same specific gravity, and you need to calculate the sizes of sometimes in the light particle, so size fractions of the light particle. So the procedure is the same only. We have the density range of 7.56 into 10 to the minus 6 meter to 4.25 to 10 to the minus 5 meter. We'll find this is again fluid. So this is the same mistake. If you copy paste the slides from first end to last end, you will do the same mistakes in all the slides. So obviously you don't need to bother about all these things. And density of particles, you need to consider density of fluid you have. Then you have to find a value of K, which is definitely below the 2.5, which is under our Stokes regime. All process is taken place. Now you have to go for the B particle. So B particle is the light particle, so you have to go for DPB1 and DPB2. Now you have the lightest particle size is a DPB1. You put 7.56 into 10 to the power minus 6. You will get the value of which is next large particle for this size, and you will get the value of 1.75 to 10 to the power minus 5. And so you can see that okay, your B fractions will have size range of 7.56 into 10 to the power minus 6 meter to 1.75 into 10 to the power minus 5 meter. This is the easiest. When you talk about the heavy particle, you have to go for the PA4 and substitute value and find the PA3, and this is the range. And you go for the small, then PB1 you have put, and then you will get a PB2, and this is the range. Yeah. Now these are the types of example which is there in the assignments, and these are and that will be asked in your exam also. Now some conceptual part which is important. One is the clarifiers and thickness, and which kind of processes, like batch processes as well as continuous process, that we need to understand. So clarifiers and thickness. Gravity separation under hindered settling condition is often used to convert a dilute slurry of fine particles into clarified liquid and a concentrated suspension. So gravity separation under hindered settling condition is often used when there are many particles, many classification example we see. Now we are seeing, we are understanding the concept clarifiers and thickness. So we have dilute slurry of fine particle into clarified liquid and a concentration suspension. These two fraction we can get after the process. This process is carried out in a large open tanks called thickness or clarifiers, and mostly in the wastewater treatment plant you will find this kind of process taking place. Now clarified liquid is free or nearly free of suspended particles, or we will make sure that our clarified liquid which doesn't have any suspended particle, and it may be reused as a process water or discharged as a waste. So this is a much more important aspect of converting the clarification of the water. This can be done by flocculation, batch or continuous sedimentation. There are mainly three processes. Flocculation is another process, batch or continuous sedimentation is more or less one process, and the type of operation is different. Like one is in the batch operation and another is a continuous operation. Now what is a flocculation? So flocculation is we have the size of particle which we want to remove from the liquid, which is very very small, or you can say it's in the micron size of diameter. The gravity settling rate will be very low for the practical separation. So this settling rate will be very low. So most of the time in the dissolved solid separation in the wastewater treatment plant, you see this gravity settling process or thickening process is taken going on 2 days, 3 days, number of days, in order to separate out the finer solid particle in a very very accurately. So, but however, many fine suspension may form agglomerates. Sometimes they are forming agglomerates in cluster of particles which can settle at relatively good rates. If they are forming the agglomerates and clusters of particles, then their mass of the particles will be increased. Okay, rather than small particles, if they are come together and make some agglomerates, then the mass will increase, and it will enhance their gravitational force interaction, and the gravitational force will help them for the settling. Agglomeration can be promoted by adding flocculating agents. So sometimes they are industry are adding the flocculating agent. They are the agents which can enhance this agglomeration process. Flocculating agents can be electrolyte. Most of the time they are electrolytes which will convert the fluid or solvent into the ionic medium, and then charged particles will be easily flocculate with each other depending on their charges. Sometimes polymeric flocculants can also be used, which are cationic, anionic or non-ionic in nature. Sometimes we are using this polymeric flocculants which has a different charge on it, and that will be useful for the agglomeration. Now settling velocity of flocculant can be very different from those of the dispersed dense solids. So settling velocity of flocculants can be very obviously from those of the dispersed dense solid. So final agglomerates have high porosity that can retain considerable amount of water that accompanies flocks while settling. Sometimes they have this kind of high porous material, sometimes they have dense material. So agglomerates are loosely bonded and sludge at the bottom of the settler compress under the weight of the additional solid. Because of size, shape and effective density of flocks which are not readily definable, it is not possible to predict settling rate or sludge density from theoretical consideration. Design of thickener is generally based on measurement of settling rates obtained from batch test in laboratories. So these are the ways we can design the thickeners for the flocculation operation. Another is the batch sedimentation operation. Here we will use the sedimentation in the batch wise. So we fill the material in the tank and we are giving the time or permitted it to the settle. So these are the mainly wastewater treatment which we discussed earlier. So equipment for batch sedimentation is nothing more than a cylindrical tank. We only require one tank with opening for a slurry feed and product throw up. So there are many sufficient openings are there in the tanks, and tank is filled with the dilute slurry and it is permitted to settle. All the dilution of the slurry we are permitted them to the settle down. After a desired period of time, clear liquid is decanted. You will get a clear liquid, you can decant it, you will get the slurry, or most of the time this, and clear liquid you will get decant until sludge appears in the drop. Sludge is removed from the tank through the bottom opening. In settling of flocculated suspension, several stages and different zones form as a sedimentation process. So there are many zones will form as soon as this sedimentation process proceeds. So we'll discuss. First, you consider this. This is a suspension of a slurry of your mixture. Consider it as a B. And after some time, let's say here is a T0, here is a T1. After some time, you will find there is some settling of the sludge particle is taken place. So it will denoted as a D. But there is in between them there is no clear-cut difference of B or D particle. You will B or D section. You will see some mixing is taking place in between. So it is considered as a C. Now after some time again, if we provide more time, then this sludge D particle size this section is increasing, has more height, and we will get this B section height will be decreasing because this will convert it into the sludge and clear liquid. So clear liquid is denoted as A. So these are the denotation. After again some time, this mostly the whole B is trying to convert or immerse into the D. Although there is some C is there, but it's not you can't understand by naked eye. So there is mainly two sections. A is a clear liquid, D is a sludge. After some time, or you can say T final, you will get the whole sludge at the thick slurry at the end, at the down, and the most clear liquid at the up. Now if we go through this same pictorial representation, then you can say this is our T1, T0, then this is a clear liquid which is starting off. So you can say after T1, T0, after T1 you can find this all four regions: clear liquid, mixture or like slurry, initial slurry, there is a blurry region, and there is a sludge section. After T2 you will find mostly these three sections: clear liquid, there is in medium, in region where sedimentary rate is decreasing and the concentration varies from initial solid concentration up to the maximum solid concentration. And then in the treat region there are mainly two different regions: one is a clear liquid, one is a slurry or sludge. Now we'll discuss about the two different aspects. There is base which we discussed is the batch thickener or batch sedimentation process. Now we'll discuss about the continuous thickener. So as a continuous thickener, you can see we already watched the videos of this kind of thickeners or clarifiers in the first place, in the first few slides. You can say feed will come, this is rotating, and sludge will be settled down over here, and it will make the thick portion, and settling soil will be going out with this underflow, and whole clear liquid will become as the overflow. So as in a base sedimentation, same zones will be present in continuous thickness. So it is a continuous. So continuously we will removing out this overflow, this underflow, and continuous we will feeding our material. So this is how this continuous thickening process is taking place. However, once steady state has been reached, where slurry fed per unit time to thickener is equal to the rate of sludge and clear liquid removal, where the slurry fed per unit time is equal to the rate of sludge removal and clear liquid removal. So then it will be the steady state process. So in continuous thickener always working at the steady state operation. So steady state operation, we need to make sure that this all three flow rate must be same. Then continuous thickness are the large diameter, shallow depth. Sorry, I made a mistake. So whatever the amount of fluid is coming out, this overflow and underflow, if we make the addition of both the flow, then it will be equal to the feed flow rate. Then continuous thickness are the large diameter, shallow depth tanks with slowly revolving racks for removing the sludges. Now this is the actual layout of this thickeners. So thickening process measurement location, as you can see, this is overflow. Here it is it is magnified and COC. Here you can see it will overflow and go into reservoir, then it will go for the clarity. It is through pipeline. At the end you will see this black region, which is a sludge, or very turbid region, which is going to the heavy duty pump is required to flow that. It is underflow. This slurry pump is required, and this is a feed, and this is a mixing. So feed is also, these are all are the feed, and underflow has this mass flow meter, and this polymer injection is nothing but the fluctuation of the process. Everything will take place, everything must be noted, recorded in order to getting the accurate data. Now this is all about the we will not discuss much detail in how the thickening design process is there. There are many more concepts are there which already taught by the professors, but we just take care of the thickening process for the clarification and classification. Sorry, there is a classification as well as clarification section on this chapter. Classification based examples are most probably will be there in your exams, or must there is another concept which is for the thickness of clarifiers. So clarifiers we discussed about the batch clarification process, batch sedimentation process, as well as this continuous sedimentation process are the same, only the operation is different. And the another thing is flocculation is also one part, where we most of the time in the industry we are combining this thickening process, sedimentation process with the flocculation process. As you can see here, we also will inject the polymer. Now if we talk about the books and reference, there's all are if you go to the some data and also you can consider the Paris Chemical Engineering Handbook. Otherwise McCabe and Smith, which is the unit operation of chemical engineering, is much more important book in this. Other than this, every time you textbook or reference book which we are used in this subject, article reverse unit operation of particles, solids, theory and practice, question and answer on chemical engineering, second volume, Jankopolis, transport processes and unit operation, and unit operation by G.G. Brown and Badger and Benchero, introduction to chemical engineering, data micro. These are the some books and references. Every time, today also we will discuss about one quotation. That is here I mentioned the quotation from the Chanakya. It's a very you can understand by reading it. So there is nothing new in it. Learn from the mistakes of others. You can't live long enough to make them all yourselves. Learning from the mistakes, own mistakes, is a very important thing, and very many successful person use this methodology to increase their productivity and success. But you can't have that much time to do the mistakes by yourselves only. So sometimes if some competitors of you or some similar background of yours someone has a similar background of yours, and are doing some mistakes, so you have to learn from them also, because every time you are not making all the mistakes by yourself, and you are learn from it. Suppose you are doing some calculation and you are not making any mistakes, but yeah, some of your friends making some mistakes, then you have to learn that okay, in future I also make to understand that this kind of mistake will be not taking place in my calculation. If it will be there, then it will be sometimes, if you okay, some we can understand, okay, overlook some problems, oh it's very easy, we how one can do so any mistakes in it. But you never know when you also do the same mistakes, which you found that which is negligible, or which is funny if you are doing mostly in the calculation and all. So you always need to learn from the mistakes of other, you need to learn from the mistakes of me, any of your tutors, anything, if he is also doing some mistakes, because we are human being, everyone can make mistakes. So if you are learning from them also, then it's fine for you to not to do that mistakes again. So you have to register that mistakes, and you have to work on it on yourself also. Now this is my mail ID. If you want to reach me out any time, you can drop an email. I can't see many participation in the online lectures or in YouTube. Mainly I think everyone knows my YouTube channel, which I have on which I am uploading these lectures. Next time I will mention this channel in this lectures also, if you don't know. But anyway, you can anytime you can go and check. So at the end, I just want to end my talk with this. Okay, so some of you are joined at this moment, but mainly I discuss all the details regarding this calculation and this some of the calculations, some of the important concept in this chapter, and some of the example problems already. So basically you can learn, you can go, you can view, you can see this video lecture, you can go to check out your textbooks, you can check out professor lecture, which is in depth and very well explain each and every small detail. So by this I am just now leaving from this meeting. I will wait for 1 minute. If someone will come and join, then I will, if someone has any doubt, I can able to solve it down. Otherwise people are just coming and going after 5 minutes of joining in this meeting. I don't know what is the purpose of it, or how much they are getting it from that kind of behavior. So better you can go for my YouTube video also. Maybe if I have time, so I can show you my YouTube videos if it is available. Wait, here if it is there, I don't think that it is there here. Okay, so I think maybe I will, the recording laptop I will show you which is the YouTube I am following. Okay, so this is a YouTube videos for NPTEL lecture. It is the link. If you search YouTube videos for NPTEL lecture, and if you go to that channel, then you will find the video lectures of this all course all chapters, sorry, 0, week 1, week 2, week 3, week 4, week 5, 6, 7, 8, 9. So this is the details of your channel, details of my channel, where I am uploading the YouTube videos for NPTEL lecture recordings. It's very easy to understand. You will just find for the mechanical operation YouTube channel. Okay, I am stop sharing this. Okay, then I want to leave you all, guys. Thank you very much for watching this lecture, or in the recorded form or in the live form.